A very good morning to all. This is Dr. Manjunath Chennapur from Anveshana Academy, Bangalore, India. Dear students, in the previous class we discussed about what is gas power cycle, how it works, what are the important four common gas power cycles we are using in our day-to-day life that we have discussed. So before going to this gas power cycles, one more cycle play a very important role. That cycle is Carnot cycle. What is Carnot cycle? What he made some assumption. Carnot made some assumption. What are the assumptions he made before developing an engine? That also we have studied. So now I will move towards next topic. Next topic, Carnot cycle. So once again I will discuss about assumptions made for an Carnot engine. So the first assumption is the piston moving in a cylinder, it doesn't have any friction. So that means what we get, dear students, he has considered an engine or he developed an engine, there is no friction. He is telling the friction between piston and cylinder is zero. That means what, there is no friction between piston and cylinder. That is the first assumption. Second one, the walls of the piston cylinders are considered to be perfect insulator. That means what, you can take the insulators, the wall of the cylinders act as a perfect insulator. Perfect insulator means what, there is no heat transfer between surrounding to the system or from system to the surrounding. That is a second assumption. Third assumption, cylinder head is so arranged that it can be a perfect heat conductor or perfect insulator. That dear students, we can take cylinder head. So sometimes it acts as a perfect conductor, sometimes it acts as a perfect insulator. How it is perfect insulator, perfect conductor, that I will explain in detail in upcoming class with neat diagram. Okay, sometimes the cylinder, sometimes it acts as a insulator also. So sometimes it acts as a conductor, sometimes it acts as an insulator. This is what third assumption what he has made. Saudi Carnot. Okay, the fourth assumption is the transfer of heat does not affect the temperature of the source or a sink. Dear students, you can see now this is a heat engine. Okay, so this is what Carnot heat engine. So here you can see Carnot heat engine. When it comes to Carnot heat engine, it is having a heat source and it is having a heat sinks now. Okay, heat sink. Okay, the heat is supplied from heat source to engine. That heat supplied is represented as a Q1. What actually is telling now, whenever you are going to supply the heat from heat source to the engine, right, the temperature will not affect. That means what, it is not going to change. It is not going to increase or it is not going to decrease because constant heat is supplied. Constant heat is supplied to the heat engine. So T1 and T2 will not, T1 will not change. Similarly, heat is rejected after the work done, heat is going to reject from the engine. That heat rejected is represented by Q2, where heat is rejected at a constant temperature. That means what, temperature remains constant. Hence, there is no effect on the temperature of sink as well as the source during heat interaction. That is a fourth assumption. Fifth one, the working media is perfect gas. Dear students, you can take when it comes to engine, right, the piston cylinder arrangement you can see here. Inside where we are having a fluid, that fluid is a perfect gas. Okay, and it have a specific heat constant. And last one is compression and expansion are reversible, whatever the piston. So here it is going to have a expansion. The piston is going to have two processes, expansion as well as compression, but these are reversible. So these are some assumptions which are made by Saudi Carnot while developing the engine. So that engine you can call it as, popularly you can call it as a Carnot engine. Okay, fine. What is that Carnot engine, how it looks, and what are the important components of that Carnot engine, that we will study now. Okay, so dear students, you can see here now, this is what Carnot engine construction. Carnot engine construction, you can see here now. What are the important components? He has developed an engine to develop this engine, he has made some assumptions that we have studied. Then what are the important components of this Carnot engine that we are going to study? Dear students, when it comes to Carnot engine, three important things we need to remember here now. First component is source. You can see here now, that is a source. That source you can see, that source having a temperature T1 and heat supplied is represented as a Q1 from heat source, and it is having an engine, that is a Carnot engine we can call, and it is going to have an heat sink. That heat sink having a temperature T2. The heat rejected from the engine is represented as a Q2. Okay, and the Q2. Okay, then work done can be calculated with the help of an equation, that is capital W is equal to Q1 minus Q2. Q1 minus Q2. This is the Carnot engine now. So now you can see now what is the important key points here of this Carnot engine that you can see now. When it comes to the first component source, right, it is having a fixed temperature, fixed and higher temperature. So it is a heat source, fixed and higher temperature. Why it is fixed? Because you are supplying constant heat to the engine, hence the temperature remains constant. It is fixed, but it is higher to the heat sink, that we have to remember. And this heat source act as an energy provider, heat energy provider. Okay, one thing. And second one is sink. Actually you can see here now, this is what second component, sink. Again it is having a fixed temperature, but it is lower temperature, lower than what? Here T1 is greater than T2. The heat source temperature is T1, it is greater than T2. The T2 is temperature of the heat sink, and it both are constant because heat added is at constant temperature, heat rejected from the engine is also constant temperature, hence the temperature remains fixed. Okay, fine. Then this heat sink act as a heat absorber. Okay, heat sink act as a heat absorber. Okay, now this is a container. The container you can consider. So yeah, as I told, in that container conducting base as well as non-conducting walls, one thing, and insulated stand, complete thermal isolation and adiabatic operation. Then working substance, that working whatever the substance what we are having in the engine, right, sometimes it will act as an isothermal process, sometimes it acts as an adiabatic process. Oh, adiabatic process. This is about Carnot engine. What is this container? How the gases consist inside it? How it becomes conducting? How it becomes insulated? That I will explain in detail with the diagram and example. Okay, as I told, dear students, where W represents work done by the engine, Q1 represents heat supplied, Q2 represent heat rejected. This is about Carnot engine. Fine. Now, so what are the important key points here now that you have to see now? When it comes to Carnot engine, the temperature difference, the first key point you can say temperature difference. The efficiency increases with the temperature difference between the reservoir. So what is that? Generally we know the Carnot cycle efficiency, that is 1 minus lower temperature. So you can take T2 by T1. Okay, T2 by T1 general temperature. Okay, the Carnot efficiency. What actually is telling now? The difference. So if assume that T1 high temperature, example 100 degree, T2 I will take it as a 20 degree. Okay, so or else you can take a 40 degree. Now Carnot efficiency is equal to 1 minus 40 divided by T1. T1 is how much? 100. So then what will happen now? Carnot efficiency is 1 into 100. It is equal to 100 minus 40 divided by 100. So then it will be 100 minus 40 is 60 divided by 100. That means what? It is nothing but what? 60%. That means what? The change in temperature, that is T1 and T2, play a very important role in the efficiency. So that is important. If the T2 having more temperature, efficiency is going to decrease. So therefore temperature difference play a very important role in the calculation of temperature efficiency. One thing. Then efficiency limitations. The whatever the Carnot engine he has suggested, right, it is 100% efficient, but it is practically it is not possible. But he limited that the engine can work at 100%. He has given some limitations. Okay, then and it is Okay, just a minute. And it is a unattainable due to thermodynamic laws. Why it is unattainable? He's telling, but he's telling 100% engine is possible, 100% efficient engine is possible, but practically it is not possible. Why? Because heat, whatever the heat you are going to supply, right, it is going to loss, it is going to loss. Just a minute. Okay, heat is going to loss in different way. Just sorry, in different way. Heat losses, you can see what are the heat losses. It will loss through water, it will loss through emissions, exhaust emissions or exhaust gas, we can call exhaust gas, we can call it will loss through radiation. Okay, one thing. And some losses will be there due to friction, due to friction losses. So these losses, when the engine will start to work, right, these losses are common. Hence, if these losses are common, there is a losses of some power or some energy. If some energy is getting lost, then we can't get 100% work. So hence, practically getting 100% efficient engine is not at all possible. That is given by Carnot. Actually, he was telling 100% efficient engine, but he has giving that such kind of limitation. But practically, it is not possible. Okay, that limitations he has given. That was the base for the other engines to calculate the efficiency. And later we came to know that 100% efficient engines are not at all possible. Okay, fine. Theoretical limit. Carnot cycle sets the maximum efficiency. As I told, he sets the engine can work maximum 100%. He is given that limit. But later the many scientists, they have calculated practically, and they came to know that 100% engines are not at all exist. But that was 100% limit was given by theoretically a scientist or engineer. That engineer, we can call it as a Saudi Carnot. This is also one of the key point. Next one, substance independence. Dear students, in the engine you can use any kind of substance. I mean, you can use gas or you can use steam also. There is no any restrictions to you to use the fluids here. Now you can use gas or steam. Then this cycle, Carnot cycle, is idealized cycle. Means Carnot cycle is a theoretical benchmark for an engine efficiency. That means what? We can take an example. So that means what? You can imagine only, you can assume only, there is an engine, you can see there is an engine, that engine will work for an 100%. This is an imagination, but you can put it as a benchmark. You can put it as a benchmark. Dear students, in your exam, so teacher will tell, so the maximum marks is 600. You keep target of what? 600 only. But getting 600 marks for all students, it is very difficult. But we can imagine, we can aim 600. But practically for all students, it is very difficult. But this is what? The 600 is what? It's a benchmark. Like that, Carnot has given a benchmark for an engine that is 100% efficient engine. But it is not practical, it is not possible. But he has given that limit. Hence, we can imagine this, that too for what? Practically it is not possible, but it is only for theoretical benchmark we can keep. Okay, fine. So now some key, now what I told, temperature difference, Carnot cycle. Hot reservoir and cold reservoir, two components it is having and two temperatures it is having. Based upon the two temperature, we can calculate the Carnot engine efficiency. One thing. And it is an idealized nature. Just it is an ideal condition. I mean, it is a theoretical, but practical it is not at all not at all possible. Okay, fine. Substance, as I told, substance independence. You can use steam or a gas as a working media in the engine. Okay, efficiency limit, but he is telling that absolute zero sink temperature. That means what, dear students? In the previous class I was telling you here, right, this is a engine. 1 minute. Okay, this is a engine. Assume that you are supplying 100 joules of energy, or else 100 joules of energy, or you can take it as a 100 degree Celsius temperature. But you want to get some work here now. That means what? What actually is telling, there is no heat loss at all, he is telling now. That means what? It is not at all possible. Zero temperature, absolute zero temperature at sink side. Zero temperature. If it is zero, then it means what? It is T1 and T2. We know already Carnot cycle efficiency. What is that? Efficiency is equal to 1 minus lower temperature divided by higher temperature. What is lower temperature here now? Lower temperature is 0. I will write it here, 1 minus 0 divided by 1 minus 0 divided by T1. T1 is 100 degrees Celsius. Then it means what? What we can write it here now? 100 into 1, it becomes 100 minus 0 divided by 100. Then 100 by 100, it becomes what? 100% efficient. That means what? If you want to get the 100% efficient, there should not be heat losses. There should not be temperature of T2. But practically it is not possible. Some amount of heat has to be rejected. So then only we can get. If some amount of heat is lost, then we can't get 100%. But he is theoretically is telling there is no any heat loss at all. There is no any temperature at the sink side. The temperature is 0, he is telling. The temperature is 0, he is telling. But it is not at all possible. Absolute zero sink is, he is telling, but it is not at all possible. Then whatever the sink is there, that is what? Waste sink actually. Okay, fine. Okay, when it comes to working of Carnot cycle, it is having 4 important process. One is isothermal expansion, adiabatic expansion, isothermal compression, adiabatic compression. That means what? 2 isothermal processes, 2 adiabatic processes. So the first one, isothermal expansion. Isothermal expansion means what? Heat is added at a constant temperature, causing expansion. Dear students, you can take a piston and cylinder arrangement. You have taken a perfect gas inside it. Okay, assume that it is a heat source. Heat source or a heat source. When you are going to bring this heat source and you are going to contact with the cylinder head, then what happens? The heat is going to transfer from heat source to the cylinder. Later it will pass to the gas. Then what happens? When the heat is supplied to the gas, what it will do? It is going, pressure and temperature of the gas is going to increase. Once the pressure and temperature is increased, the volume, what will happen? Volume is going to increase. That means what? When it is pressure is increased, that explosive force is going to act over the surface of the piston. Hence the piston will start to move from this point to this point. That means what? It will start to expand. So that process, because of continuously heat supplied, constant heat, that is Q1, the piston is going to create, the gas is going to create an explosive force over the surface of the piston. Hence the piston is started to expand. That process we can call it as a isothermal expansion. At a constant heat supply, the piston is getting expand. That is what? Isothermal expansion. Okay, so now second one, adiabatic expansion. Adiabatic expansion means what? Once the heat is supplied, then immediately we will remove the heat source and we are going to put an adiabatic material, adiabatic wall we can call, adiabatic wall. That means what? That wall will not allow to transfer heat from system to the surrounding or surrounding to the system. Immediately we are going to bring this material, this wall, and we are going to contact with the cylinder head. Hence there is no heat transfer at all from inside to the outside or outside to the inside. But still, because of the heat contained in the gas, that is going to create the explosive, still it is going to create the explosive force over the surface of the piston. Still the piston is going to expand. The piston is expand, but there is no heat transfer from surrounding to the system or system to the surrounding. The piston is expanding. As I told, as one assumptions we made, the piston is already well insulated. That means what? Completely it become well insulated, but the still is going to getting expand. That process we can call it as a adiabatic expansion. What is adiabatic expansion? There is no any heat exchange or heat transfer, but still the piston is getting expand. That we can call it as a expansion process. Okay. Next, third one, isothermal process. What is isothermal process? That we can see here now. Okay, now this is process expansion is done. Now assume that piston is at this particular point. I am going to compress it. Now you can take this point piston only. You are going to compress it, right, one by one. So now what I will do, isothermal compression. I will remove this adiabatic wall. Again I will bring in contact with the this diathermic wall, we can say, or the heat conductor. So as a heat conductor, when you are going to put that heat conductor, right, when you assume that this heat conductor is moved in this particular point, it is contacted with this. When you are going to compress it, right, the heat is going to generate inside the cylinder. That means what? Gas. That heat is going to transfer to the diathermic wall or heat conductor. Then that heat is going to reject, or heat is going to release. That heat is releasing, that heat can be represented as Q2, but it is constantly heat is removed or rejected from the system or from the cylinder. That we can call it as a isothermal compression. The compression process is happening because of happening, hence the heat is generated because of that heat is rejected from the cylinder at constant temperature. Then that we can call it as a isothermal compression. So immediately what I will do, third process it is. Okay, immediately what I will do, I will remove this diathermic wall. I will put an adiabatic wall again. Adiabatic wall, adiabatic wall, adiabatic wall, I will keep it immediately. Then still the compression process is happening, but the heat is not at all transferring from system to the surrounding, but compression is happening. That process we can call it as a adiabatic compression. What is adiabatic compression? The fluid or gas is compressed without heat transfer, but temperature gets increased. That process we can call it as a adiabatic compression. So when it comes to Carnot engine, there are four processes: isothermal expansion, adiabatic expansion, next isothermal compression, next adiabatic compression. These are the four processes are very important. Based upon these four processes only, he explained the Carnot engine. Fine. Now I will try to initially piston is at particular point 1. Okay, when we are going to bring this heat source to the cylinder, right, with the help of diathermic wall, the expansion is taking place. That expansion we can call it as a isothermal expansion. At what temperature it is getting expand? T1, at a constant temperature. What we are doing now, we are supplying certain amount of heat as an input, that is what? Q1. Okay, once it reaches point 2,